All right, so let's get started. Welcome to this week's CITP seminar. We're fortunate to be joined by Lucy Chin, who's a PhD student in computer science at Brown, working with our good friend, Seni Kamara. Today, Lucy is going to be talking to us about work on the important issue of gun safety and ways in which it might be possible to reconcile the values of firearms registration with privacy concerns that have been raised around those types of registrations. This is a project that appeared recently at the IEEE Symposium on Security and Privacy, known to many folks as Oakland, although it's not actually in Oakland these days. Before handing things over to Lucy, I just want to note at the outset how good it is to see this model of work that is far too rare in computer science. And it is wonderful that Lucy's exemplifying it in her PhD research, where computer scientists are directly engaging with government, here a congressional office and other stakeholders on firearms safety, and then using computer science methods to understand the range of options that might be available to government and other stakeholders. Again, far too rare, something we try to do at CITP, and it's wonderful Lucy's doing in her PhD research. Lucy's going to pause for questions at points in her presentation, and then we'll have a Q&A at the end. And this will be recorded as well. Okay, with that, I'm going to hand it over to Lucy.
Awesome. Yeah, thank you so much for having me here today. I'm particularly excited to share this work with you all. So I will start screen sharing now and get started. Okay. Oops. Can you all see? All righty. Awesome. Yeah. So as Jonathan mentioned, today I'm going to be sharing work on a decentralized and encrypted national gun registry. And this is joint work with Seni, Tariq, and Andrew, who are listed here. So at the top, I just wanted to note that in the United States, while we have been dealing with this pandemic that's been going on, the epidemic of gun violence has also worsened. So particularly this past spring, this seemed to capture more of our national attention as we witnessed what felt like one high-profile tragic shooting after another. And we've also seen an uptick of gun violence of every kind. And with that, we've seen increasing support for gun control measures, as well as more recent legislative focus on addressing gun violence. So today I'm going to be talking about one legislative proposal addressing gun violence and our work in assessing its feasibility. But I wanted to say up top that we're not claiming that technology will magically solve anything or that any one policy will fix gun violence. So we want to, we recognize that this is underpinned by some much deeper issues, for example, those related to racial justice or healthcare or these economic disparities that exist in the US. So when a tragic event does occur, such as a mass shooting or a homicide, if there is an unidentified firearm found and more information is needed, detectives can go out and try and figure out who previously owned the gun by performing a trace. And they can do this using a serial number of the gun and other characteristics of the gun. And tracing is done at the National Tracing Center in West Virginia. And this actually involves employees physically searching through file cabinets and boxes full of forms, as you can kind of see in these pictures. And this on average requires 4 to 7 business days. So typically speaking, 400,000 traces occur in 1 year, and only 65% of those traces can even be answered. And as you see here, we currently don't have an efficient means of tracking the sale and ownership of firearms. So this inefficiency that I described is also intentional. Under the Firearm Owner Protection Act of 1968, we actually can't have a centralized national registry. So therefore, the existence of some database that is searchable would violate this law, which the acronym is FOPA. And that brings us back to the file cabinets full of records that we saw. Okay, so with that, the focus of this talk is on a specific legislative proposal. This legislation was drafted by Senator Wyden's office of Oregon. And this was done the draft legislation was done in 2019. And it proposes a decentralized and voluntary national gun registry that explicitly guarantees data privacy and local control over data. And this was envisioned as part of broader gun control laws and to help support a background check system, as well as assist with that gun tracing process we saw with the warehouse of the file cabinets. And it's designed explicitly so that it doesn't violate the Firearm Owner Protection Act while also allowing for a digital searchable database. Okay, so when Senator Wyden approached us with this idea, they had a specific question they wanted to ask. So they were curious whether a decentralized encrypted national gun registry like this could be possible at the scale of the United States, and if the legislative requirements they had conceived could actually translate to concrete cryptographic protections. And our role here as cryptographers was to answer these specific questions about this specific piece of legislation. So again, gun violence is an extremely complex issue with different avenues for making change. And that includes addressing those underlying issues I mentioned or passing statewide reform. So we recognize that federal gun reform is only one piece of this puzzle, and it is one that has been prone to stagnation. So when we first began this project, our expectation was not necessarily that the system would be instantiated. Our hope is that this work helps foster a dialogue about what trade-offs are possible in realizing a national gun registry for when and if there actually is a right time to have this conversation. So to begin, I'm going to discuss at a high level what a system like this actually would look like. And as I mentioned, a key property is that all of the data is encrypted and locally managed. So for a single state, let's just think about perhaps California. Each county would designate a local official who holds a key. And this key is used to encrypt license and registration data for that county. And that is stored in that county's own encrypted database. So if you see here, we have a bunch of local officials who have their keys, and corresponding to that, the encrypted local database for that county. Okay, so each state then operates a server which stores all of the encrypted local databases for the counties. And the only role of this server is to store data and to maintain its availability. And then all the counties would send their encrypted databases to the state server. So if you look at this picture again, we have California and its state server, and it has all of its encrypted databases. And without the keys for them, the server can't actually access any data. So if we abstract this out, we have the California state server, which holds data for some number of its counties, and then all its local officials who hold keys for the encrypted local databases. And then around the country, for each participating state, there would be a state server holding local data for all of its counties as well. And here I want to emphasize the voluntary aspect of this. So each state would have varying numbers of local officials, with new ones choosing to opt in and opt out at any point. And they are able to do so without affecting the ability of other localities to participate. And this then also gives flexibility in terms of local governance. So different states and localities can pass their own laws dictating whether or not to participate in the system. And these localities can also decide at any later point to revoke access to the locality's data without affecting any other parts of the system. And then together, this composes a gun registry that is a system of decentralized, locally managed encrypted databases that can be queried by authorized users across the country. So now that I've talked about the high-level goals, I'm going to address the system requirements based on the draft legislation. As I mentioned, the first thing is that each county designates a local official who is responsible for an encryption key. The encryption key is required to view, query, update, and encrypt county-level data. And then authorized users are permitted to query the system for registration and licensing data. So this might be a detective or local official from another state who wants to perform a trace, or it might be a distributor who might want to see if an individual has a valid license before they're able to purchase a gun. And then attempts at collecting large amounts of information are prohibited, and this will be regulated on the locality level based on factors that they determine. And this might be something like the population of the locality. And then 5, authorized users must be able to make queries even if the designated local official's key is offline. And this is just for some pre-specified amount of time. And it's necessary since when we just think about the United States, we have many different regions that vary in different levels of internet connectivity. So if there were to be unstable internet connection for some locality, data from that locality should still be accessible. So once a key has been offline beyond that pre-specified period of time, data pertaining to the county should be completely inaccessible. And this again just allows counties to opt out of the system without affecting the ability of other counties to participate. So this kind of concludes the part where this concludes all of the system requirements. So I wanted to kind of pause for questions and see if anyone had any things they wanted to clarify before I move on to the protocol.
So Lucy, maybe it would be helpful for folks to give a quick comparison to a centralized database or a federated database system, sort of what the key advantages are in comparison to those designs, which might be more familiar to folks who are watching the presentation.
Sure. Yes. So, right. In a centralized database, you kind of have the digitized version of that warehouse, I guess, where all of the records are being centralized in one place. They are accessible to everyone, but the storage is maintained in that one place. And as I kind of mentioned with the Firearm Owner Protection Act, that is not actually legal and is something that would or might be more prone to violating the privacy of gun owners. And here, the key thing is that every single county, all of the data is within that county database. So the control of who gets to access that data, who is managing that, editing it, updating it, it's all going to be held within that county. So the key idea there is that, if that county decides that, okay, we don't want to participate in this anymore, they can just take their data offline and they have a lot more agency over how that data is used. Instead of, if you're in a if everything's in a centralized database, it might be more difficult for you to have that direct access here because you have an explicit guarantee here that you can remove that data, and you have the explicit guarantee here that all of the accesses to that data is being controlled by someone within your county. Yeah, so I think that is the key difference here, and it is that key difference that actually allows for something like this to exist versus a different type of database that would violate, the FOPA laws. Alrighty, I will move on then. Okay, so how do we actually build this sort of system to realize the system requirements that I talked about? We leverage these following cryptographic building blocks. So the first is secure two-party computation, structured encryption, and secret sharing. So secure two-party computation, or 2PC, allows for the computation of a function over private inputs from two different parties while producing some public output. So here, neither party learns the other party's inputs, but one or both parties might learn the output. And then secret sharing allows a party to split some secret into what we call shares, and then these can be used to recombine the original secret based on some threshold. But the shares on their own do not reveal any information about the actual secret itself, not even partial information. So structured encryption allows for a user to encrypt a data structure, store it in an untrusted environment, and perform private search queries on top of that data. And this is done using the encryption key to generate tokens that are specific to the query. And these tokens are sent to the server, who then returns the response without knowing what the query was. And here, the data structures that we're using for structured encryption are dictionaries and multi-maps. So as you see here, dictionaries map labels to values, and a query for the label W3 here returns ID2. And multi-maps just map labels to tuples. So the key difference is that for every label, there are now multiple values. So if you're going to request the W3, what comes back corresponding to that is now ID2 and ID6. Okay, so for simplicity, let's just take a look at the encrypted dictionary. As I mentioned, structured encryption works on any type of data structure, but here is just an example we're going to focus on, which is the dictionary. So in other places of our protocol, we also use encrypted multi-maps. And for the construction we use here for encrypted dictionaries is the pi-based construction, which was published by Cash et al. In 2014. So for setup, the function takes in a security parameter and a dictionary, and the output is an encrypted dictionary and a key. So I mentioned these tokens before. The token generation function takes in that same key that was produced and a keyword. And what it outputs is a token. And we can think of this token as an encryption of the keyword that was given as input. And the get function then consumes this token and the encrypted dictionary, and the output is the encrypted response to that original query, which was the keyword. So here it's W3, what's being returned is the encryption of ID3. And our implementation returns an encrypted response, but there are other constructions where the response is in the clear. So with related work, there is precedent for national gun registries, but none that have the same set of security and privacy guarantees that we have outlined here. So Canada operated a national registry, and a key criticism was that the data was centralized. And then New Zealand passed legislation in 2019 for the creation of a registry. And individual states also have their own versions of registries. And there are also some superficial similarities to note with federated encrypted databases. So this includes Conclave and SM-SQL. And these are just two systems that also leverage secure computation for private query execution over databases. But in their systems, the query is evaluated on the union of data held by all the data owners, whereas here, once you identify a database, the query only needs to be evaluated over a single data owner's data, and I will show you what that means. I'm going to describe our protocol, but wanted to add that it's one of many ways to fulfill the requirements of this draft legislation. So this design, however, received positive feedback from members of Senator Wyden's team. And in the interest of time, I'm going to be focusing on just the querying process. So the full protocol is described in our paper if you are curious. Okay, so let's just pan back out to this global view. We have all of these state servers and they hold encrypted local databases. And then let's say there's some gun distributor who wants to check if an individual has a valid license to be able to purchase a gun. They would know exactly which local county database to query, and they can make a query to that local database directly. But if we consider another user, and if we go back to that tracing example we had, let's say we have a detective who found a gun but wants to know what county it originated from and wants to get additional information about it. So they wouldn't necessarily know which county that gun originated from. That is the nature of their query. So they're not able to directly query that local database in California per se. They now have to actually figure out which county to even request that data from. In the worst case scenario, they would have to query every database in all 50 states, and that is pretty inefficient. So to prevent against this scenario, we introduce something that we call an encrypted global directory. So here, this encrypted global directory contains key value pairs and of serial numbers to county IDs. And we want to store this information in a centrally accessible place, but we don't necessarily trust a server to have access to this information. So therefore, we're going to encrypt it using a structured encryption scheme. And I want to emphasize here that in this centralized place, we're just storing the serial number to county IDs, and that is it. So, okay, this just enables a user to now make encrypted queries in the form of an encrypted serial number and get an encrypted county ID as a response. It prevents a user from having to do that query to every single county database in every single state. And it also operates such that the server doesn't know what the queries or the contents of the response are. However, we still don't trust a single entity to hold the encryption key for this encrypted global directory because it does contain every single serial number to county ID mapping. So therefore, we also introduce these two custodians whose role is to hold shares of that encryption key. And their only role is to just hang on to those shares and to be online to service requests. We also make the assumption that they're going to behave semi-honestly and not collude with one another, and they should be chosen so that they don't have any incentive to collude. So one example we had in mind was perhaps two organizations that are politically opposed, maybe the NRA and ACLU, but there are also other examples within our government that we can maybe think of. So, okay, to begin this process, let's say a user has a request for a county ID corresponding to a serial number. So here we just have the serial number 1, 2, 3, 4, 5, 6, 7, 8, 9. The user is going to first secret share their serial number into two shares, one for each custodian. And then the custodians are going to participate in a 2PC for generating that query token we talked about for the user to be able to retrieve the county ID. So the custodians first begin by inputting their shares of the serial number and key into the 2PC. As a first step, the serial number and key are reconstructed, and then they're going to serve as input for the encrypted global directories token generation function. And this comes from the structured encryption scheme. So this then produces a decryption key and token. The token is used by the server to return the correct encrypted county ID, and the decryption key is used to actually decrypt the encrypted county ID once it comes back from the server. So it's important to note here that there is a unique decryption key per serial number and county ID pair. So every time there is a request, this decryption key does need to be generated for every unique serial number request. Okay, so we don't want the custodians have access to the decryption key or token either. So the key and token are then secret shared. And these are outputted back to the custodians. The custodians then pass the decryption key shares to the user who reconstructs the key. And the custodians pass the token shares to the server who reconstructs that token. So once the server receives a token, the server is able to retrieve the corresponding ciphertext. And the server then returns the ciphertext containing that county ID. So here it's just the encryption of county ID 0001. And then using their decryption key, the user can now decrypt and obtain that county ID they were looking for, which is 0001. Okay, so going back out to this view again, the user now knows which county to query in order to receive that full record they were looking for, right? So right now they just know the serial number and county ID pairing, but they want to actually get information about that gun owner. At this stage, the user can now make a direct query to the specific encrypted local database that it just identified. In this case, it was county 0001. Perhaps that is a county in California. Okay, so to just take a look at these encrypted local databases, each record in a database is going to contain some basic information about a gun owner and their firearm. And this might be the owner's licensing ID, additional details on the gun. If you see here, we have Christopher Smith, who owns some gun with a particular make and model. We also have some information on Christopher Smith, like his address and birth date. And a user who's making queries to this database can make different types of Boolean queries on the data. So this could be a simple query with just a single keyword, as you see here, just asking for the serial number, or more complex disjunctive or conjunctive queries. So these are some examples of queries, but based on a county's rate limiting practices, these queries might not actually be valid, depending on the volume of records returned. So yeah, if you remember, being able to limit these sorts of bulk queries is a specification of the draft legislation. So for example, with the second query, perhaps querying on the keyword address might not even be allowed as a whole under rate limiting practices of a specific county. Perhaps, 1,000 individuals live at this address and the volume of records returned would prevent it from being valid by nature of the volume. So the point of the slide is to kind of demonstrate what is possible in terms of query expressivity and not necessarily what would be definitely allowed as a query. Okay, so to begin the querying process here in the local database setting, where the user has now identified which database they want to make a query to, the user has their query queue and the local official has that key we've talked about before. And to begin the querying process, these parties must participate in a 2PC. So this just keeps the user's query and local official's key private. And in this 2PC, the query and key serve as inputs for a token generation algorithm. And again, this is going to come from the encrypted local databases underlying structured encryption scheme. And this again produces a token. So the token is outputted to the user and that user forwards it to the state server. And the state server then returns an encrypted result for that query. So here we have the encryption of file a.txt. So in order to decrypt the ciphertext, these two parties have to participate in another 2PC. And the inputs here are now the ciphertext, file a.txt, and the key. So First, a decryption key is going to be generated using the record ID of the ciphertext and the official's key. In this case, the input would be the string file a.txt and the official's key. And then we call the function for generating this resulting decryption key the resolve function. This decryption key is then used to decrypt that ciphertext, which is returned to the user. So the user now has the record in plain text that they were looking for, and this concludes their querying process. So I want to point out here that the local official does learn the number of ciphertexts that are inputted into this 2PC, but nothing about the contents. So they can then conduct rate limiting by refusing to decrypt if the number of ciphertext is too high. There can also be additional checks that you place in here into the 2PCs, either of the 2PCs we talked about, for more sophisticated rate limiting. So let's say that certain types of keywords on their own can't be used as single keywords. Like we talked about, maybe you can't make any query on just the address alone, or maybe just the first name alone, since this would return too many results. So that logic could be incorporated into the 2PC here to check the keywords prior to actually generating that token. So these are just some ideas of rate limiting that would be part of future work if this were to actually be implemented and deployed as an actual system. Okay, so this kind of concludes the protocol section of my talk. So I wanted to pause here for questions if people had questions specific to the protocol I've described. Okay, seems like there are no questions, so I will move on. Okay, something I mentioned at the beginning is that if a local official is offline, users should be able to make queries pertaining to the data for that county. So what actually happens when this local official is temporarily offline? To maintain access, the local official designates 3 helpers who the official trusts, and they would likely be other local officials, perhaps within the same state. So using 2 out of 3 Shamir secret sharing, the local official is going to secret share their key with these helpers, who can then fill in for the official to provide offline access. So instead of the local official, the helpers would participate in an MPC with the user. As a first step, the encrypted local database's encryption key is reconstructed inside a secure multi-party computation that's just going to reconstruct this key using Shamir secret sharing. So as I mentioned, this has to include at least 2 out of 3 parties. Okay, so one of the helpers is designated as the computational delegate, and this party's role is to continue to be online for the remainder of the querying process, while the others may now exit the protocol. And at this point, the protocol only involves the user and the computational delegate. Since neither of them can have access to the actual key, the key is secret shared back out to the user and the delegate. And the key share here is different from the one the computational delegate received from the Shamir secret sharing originally with the local official. So if you note here, this key share is going to be the result of an XOR secret sharing scheme that just involves these 2 parties. So these are fresh key shares. And if you recall this 2PC that was part of that querying process, the difference here is that instead of the local official, we have this computational delegate. Now, both the user and the computational delegate have to input their shares of the key as a first step of this 2PC. So instead of being inputted, the key is reconstructed inside that 2PC. And the computational delegate will now perform the rest of this 2PC with the user, and that results in the token being outputted as it would in the original setting. And if you remember, there was a second 2PC performed in order to decrypt records. So again, the delegate would remain online and perform that 2PC as well with the user and provide its key share as an input. And at the beginning of the talk, I mentioned the importance of being able to remove these local databases. So this can simply be achieved by erasing the local official's key. Without it, no querier would be able to access data pertaining to the locality. And this is just because without the local official inputting their key into these 2PCs for querying, the query would simply not work, and all data pertaining to the locality within the server would be completely useless. So in practice, we also envision this key to be some sort of a hardware token, maybe like a YubiKey. So it would remain connected to the local official's device. And this would allow a local official to simply physically remove the key in order to shut off access. Next, the local official would then have to ask their helpers to also erase their key shares. Assuming they're trusted by the local official, they would simply just erase them. But to provide stronger guarantees, the local official could use a mechanism for key rotation. So once the original key and at least 2 out of 3 shares of the key are erased, the encrypted local database is now entirely inaccessible. All right, moving on to security. The legislation implicitly defined trust relationships that we extracted and formalized into a threat model. We only consider security against semi-honest adversaries and construct security in the ideal real-world paradigm where we make comparisons between the execution of our protocol in the real world and the execution of an ideal gun registry functionality that we define. And we tolerate the following corruptions, which we categorize as external or internal. So for external, we tolerate the corruption of the server and one of the custodians, and then for internal, at most one local official. So full proof is in the extended version of this paper on ePrint. Okay, so the leakage here is based off of the encrypted dictionary and encrypted multi-map constructions that we use. And for the encrypted global directory, initializing the encrypted global directory doesn't leak anything, and but adding to it does reveal the number of updates per identifier. So if you think back to the identifiers, those were the serial numbers, but so what this means is that every time the same serial number is updated, the server learns that some encrypted label corresponding, its corresponding value has changed, but it doesn't know what that serial number is or what the corresponding content is. So for queries, the server does learn the query equality pattern. And essentially what this means is just that the server learns the number of times some serial number is queried, but doesn't actually reveal what the serial number actually is. And then for the local databases, this does get a little bit more complicated, but initialization still doesn't leak anything. Adding to it leaks to the server the number of total records in the database. And then for queries with a single keyword, let's say the query is just first name Chris, the leakage is the query equality pattern, which I discussed. But there's also something called the response identity pattern leakage. So this just reveals the record IDs in response to a particular query. This doesn't leak the query or the records. And then for disjunctive queries, for example, first name Michael or first name Mike, that would be the query. The server learns the query equality pattern of all of the keywords in the disjunction and the response identity pattern. And then for conjunctive queries, you can refer to the paper. It's a bit more complex, but the important consequence of the leakage for it is that the server would learn the record IDs of records that share a specific set of keywords from the query and the frequency that they're accessed. So they do not learn the query or the content of the records. And again, this leakage comes from the specific constructions we use, but our protocol is designed in a black box manner that doesn't depend on these specific construction choices. So as there are advances in the space and implementations of structured encryption that have lower leakage or even close to no leakage, they could be used in place of what we had here. All right, so an important piece of this work was to evaluate if this was possible at the scale of the United States. So we therefore implemented the protocol end to end and then ran experiments based on the estimate of the number of guns in the United States. And we also did a basic cost analysis to confirm the financial feasibility of running a system like this, which is in the paper. But I guess the summary of that is, yes, it is cost effective to run something like this. And this was important if you recall back to the Canada server. A key criticism there was that it was very costly and people did not feel that it was effective for the cost that it had. So in implementing the system end to end, we leverage many different libraries and frameworks, which I've noted here, as well as the implementation tasks that were completed. And a key thing to note is that we implemented HMAC SHA-256 for use within 2PC, and this was done within the EMP toolkit framework. And then for structured encryption, we use implementations through the collusion library with some modifications to the PRFs that were used in token generation and the encryption scheme for encrypting records. And then for Shamir secret sharing, we use the existing protocol within the GIF framework and then implemented XOR secret sharing. And then we just use Node.js to glue all these separate pieces together and to handle communication between the different parties as we're doing this evaluation. So I want to highlight a few metrics, starting with the encrypted global directory. Here on the x-axis, we have the number of serial number county ID pairs that are already in this encrypted global directory. And this shows that the time it takes to add a single pair into the dictionary is independent of the number of items that are already stored in it. We were interested in looking at what happens when there are 400 million pairs specifically in the global directory, since that is the estimate of the number of guns in the United States, and this is according to the Small Arms Survey. And it would take 377 milliseconds to add a pair with that 400 million pairs already in the directory. And then the time it takes to find a county ID is also independent of the number of pairs already in the directory. So on average, it takes 247 milliseconds to find a county ID with 400 million pairs in the encrypted global directory. And as the encrypted global directory grows, it doesn't actually impact the time it takes to add a pair into the directory or the time it takes to find a county ID in the directory. And if you observe here for both operations, 2PC, which is the clear bar, takes up the bulk of the time. Okay, so moving on to the encrypted local databases, it takes less than 4 minutes to add 100,000 records here. And for query performance, the query time depends on how complex a query is and the number of records returned as a result of that query. So this chart shows that it takes less than a minute to respond to a query that returns 100 records. And a query returning this many records likely would not be valid, but we included this metric as a demonstration of the performance of the system. And if you see here, 2PC decryption encompasses almost all of that query time. And to take a closer look at the query times, this shows the query times with the 2PC for decryption removed on local databases of varying sizes. And we evaluated on 3 different queries and generated fake data so that these queries always returned a preset number of records. You'll notice that the query returning 10 records takes longer. And this is because the query is more complicated since it involves 2 different addresses. So the 2PC just takes a bit longer here. This also shows that the query 2PC time is a function of query complexity, and the more keywords and conjunctions or disjunctions there are, the more computationally expensive that 2PC will be. But that being said, as we saw, the 2PC for decryption still takes up the vast majority of that computation. And then lastly, for storage, it would require 110 gigabytes to store 400 million serial number to county ID pairs in the encrypted global directory, which for a database for this size is not that much storage. And then using the set of keywords I had previously shown when describing the local databases, if you think back, this included basic information about a gun owner, like their name, address, birth date, information on the gun. It would take 1.7 gigabytes to store a local database with 100,000 records. So this kind of brings me to the end of the talk, but before I conclude, I wanted to acknowledge that introducing a protocol designed specifically for data collection by law enforcement does have the potential for abuse. In the case of driver license and license plate databases, they've been used beyond the intention of their collection for targeted deportations by ICE and facial recognition algorithms by the FBI. And we kept this in mind when thinking about how the data stored could be misused. While we can't control how this protocol would be deployed if it ever were to be deployed, we strongly advocate for policies and regulations that limit personal data collection by law enforcement and full transparency on access control. New developments in cryptography as a whole can enhance privacy, but the use of privacy enhancing technologies can also be used as cover to request access to more and more data. Therefore, we believe that policies and laws that specifically outline and communicate clearly to the public what kind of data can and cannot be collected before a system is built and deployed would help deter potential for abuse. To conclude, we designed, implemented, and evaluated an end-to-end encrypted national gun registry explicitly using draft legislation. So this work shows that it's possible and practical to run a system like this at scale. And in working with Senator Wyden's office, we hope that this collaboration will encourage more of its kind between policymakers and technologists. So I'd like to thank their office for sharing this draft legislation and for providing valuable feedback. And thank you all so much for listening to this talk.
Lucy, thank you so much for joining us. A terrific presentation. Sunny, thank you for the guest appearance. And we look forward to seeing more great things from your group.
Awesome. Yeah, thank you again for having me.
You bet. Take care.
All right, bye.